You probably know because you looked it up. I don't like that.
Okay, reaction mechanisms today.
Oh, winter dreams.
So, we got a lot of vocab here on this little slide. Okay? What we have, let's say I've got, well, I'll kind of show this on the next slide. Okay, a reaction mechanism is the series of steps that make up a reaction. I alluded to this the other day, that most balanced chemical equations do not happen in one step. They happen over a series of steps. If they happen over a series of steps, they have a name that's called a reaction mechanism. The steps of a reaction mechanism also have a name. What are they called? Elementary steps. And I'll show this on the next slide. Okay? The slowest step of your steps is called your what? Determining. Okay, what do you think rate determining means?
Determines the rate.
It determines the rate. Now, have you ever heard you're only as strong as your weakest link?
Yeah.
You're only as fast as your slowest step. Right? So if I have 3 steps, and one step's really slow and the other steps are fast, it doesn't matter if those other steps are fast, you're only going to go as fast as that slowest step. It's like you can only put so much water through a funnel, right? That makes sense? You can keep pouring water in, but only so much is going to go through that funnel.
Even that.
But even then, it's still only going to go as fast as
it down like that.
But it's still only going to go as fast as that funnel.
It's a pipe. It's a pipe.
Okay?
It's got a little divot.
This is, I don't want this to confuse you. All this simply means is if the reaction takes multiple steps, it is called a complex reaction and has a reaction mechanism. You don't get confused by, because technically these two things seem similar, don't they? Okay, if it has multiple steps, it is a complex reaction, and if it's a complex reaction, it has a reaction mechanism. Okay? And I'll show you how an intermediate works. It says an intermediate is the product of one step, but then gets reacted in the next step. So if it's a product in one step, and then goes bye-bye and gets reacted in the next step, is it going to appear in your balanced chemical equation?
No, that's a bye.
You say bye-bye, go bye-bye. And these reaction mechanisms are affected by the temperature. We're not going to get it. Actually, writing reaction mechanisms is really quite difficult. And it takes actually a pretty high-level chemist to be able to predict a reaction mechanism. So the stuff that we're going to do is going to be based on more vocabulary and understanding what this stuff is. Okay? So here is. You guys remember Hess's law?
Yeah.
Okay. This was an example of a reaction mechanism. Okay? So is this a complex reaction?
Yes.
How do you know it's a complex
It
reaction?
has multiple steps.
Because it has multiple steps. If it's a complex reaction, it has a reaction mechanism. So, the sum of my steps are called the reaction mechanism. Each individual step is called a what?
An elementary step.
Elementary step. If you have a step that gives you a product, and then the next step reacts that product, what are they called?
I forget. It goes bye-bye.
Intermediates. Okay? You guys know what an intermediate is. Okay? Here one day, gone tomorrow.
Intermediate.
Okay? So it's a complex reaction because it has more than one step. If it has more than one step, the series of the steps has a name. It's called a reaction mechanism. Each individual step has a name. It's called an elementary step. If one step creates something and the next step makes it go bye-bye,
It's intermediate.
it's an intermediate. There it is.
So many words right now.
What?
This is a lot of words.
It is a lot of words.
Go back and
But once you look through it, I think you'll understand that these vocabulary words aren't overly difficult. It's not like we're thinking deeply, it's just new words. Okay? So here's just showing you that if you have a different temperature, you could have a different reaction mechanism. So if you look at this, is the overall net balance chemical equation the same from the previous example I just showed you? Maybe you weren't looking close enough.
Yes.
But in the previous example, it was I2 plus H2 gives you 2 high. Okay. So it was the same beginning as it was, or ending as the other one. So all this is trying to show you is, okay, still a complex reaction because it got more than one step. The reaction mechanism is different because the series of steps are different. Okay, and the reason why the reaction mechanism is different, or the only way you could get a different reaction mechanism, is if you have a different temperature. Now, are you guys going to be able to predict reaction mechanisms? No, that's much higher level. All right, rate laws is going to be the remainder of today.
Let's
Focus.
We don't know where we're supposed. Oh, they were both circling.
All right, on to stuff that actually matters. Let's show how, what we're going to do with rate laws is we're going to show how the concentration of reactants are going to be affected over time. Here's a couple things that you must know. First and foremost, you must know this. Make a star by it. You can only discover the rate law doing it experimentally.
Are we gonna do that?
You want me to try to keep you up, or just leave it?
Mr. Kramer, I went to bed last night at 7:15.
Wow, okay. On to something that's important.
That is important.
Okay? So quickly some stuff to kind of point out here. What do the brackets mean? I think we've talked about this in a different chapter. You guys remember?
Concentration.
It means concentration.
Concentration.
Well, molar concentration just means the molarity is our concentration. But anytime you see brackets, it's the concentration of those particular reactants. So, rate laws will have 3 things. Okay, this will be the rate, what you actually compute. This is an experimentally determined constant. You need to write that down somewhere so that you know that K is an experimentally determined constant. Hence why we have to find the rate law doing experimentation. So we are actually going to write rate laws from experimental data in a sec. Okay? Then it will have brackets representing concentration of reactants. Now you may have a reactant that does not affect the rate, and we'll talk about that in a little bit. Things I want you to know. They're always going to have an experimentally determined constant. They're going to have brackets representing concentration. Now you aren't going to see products in the rate law because the best way to determine a rate law is to determine it right at the beginning of the reaction. And at the beginning of the reaction, do you have any products? No, you don't have. If you right before you've reacted anything, do you have products? No. Okay. Okay. I'm going to kind of show you this relatively quickly. It'll make more sense when we apply it and use it. Okay. It says a reactant does not appear in the rate law. If it does not appear in the rate law, it's said to have 0 order. So I'm going to use this as my kind of template example here. I2 plus H2 goes to produce 2 high. Okay? So, an example of a rate law where I do not have a particular reactant in it would look like this. Let's say I2 didn't have an effect on the rate. What I mean by this is I could change the concentration of I2 all I wanted, and it doesn't change the rate. It's not even going to be in the rate law. Okay? The second part says if a reaction does appear in the rate law, but doesn't have a sub or an exponent, it's said to be first order. Let me explain what I mean here. So what I have here is I2 in this rate law right now. So what is the order of I2? 0 order. Okay? H2 appeared in the rate law, but doesn't have an exponent. What's its order?
First order.
Oh, no, then I could exponent 2 would be semi-equal.
So let me go on to the next slide. You can have up to second and potentially third order. So let me write a rate law for this, where it would be second, maybe third order. Rate equals K. We'll say H2 is second order, and I2 is third order. It would look like that. You're probably wondering, what does that mean? Well, it's how much a particular reactant is going to affect the rate. Because didn't we say we could change, we could increase temperature, we could change, couldn't we change the concentration to affect the rate? And we said if we add the concentration, it usually makes the rate what?
More fast.
Go faster, correct? Some things make the rate go faster than other things when you change their concentration. So, if I have a rate order of 3 versus 2, which one is going to change the rate more when I increase its concentration? The one that has third order. Does that make sense? The one that has first order, so for example, if I double the concentration of H2 in a first order reaction, the rate's going to get doubled. Okay? If I double the rate of a second order reaction, the rate's going to go up by a factor of 4, 2 to the power of 2. What if I double something that's third order?
Power 3.
2 to the power of 3 would be what?
Oh, awkward.
8. So it would affect the rate, make it 8 times faster. So you're probably wondering, why would a reactant not affect the rate law? Here's what's important. Remember we said there was a series of steps, correct? Okay? Right, a reaction can have a series of steps. It's called a reaction mechanism, correct? And then we said there was a step that determines the rate. What did we call that? The rate determining step. We said we're only as fast as our slowest step. So what if one of my reactants isn't in the slowest step? Yes. If this reactant is not in the slowest step, I can change the concentration all I want, and would that affect the rate at all? No. Okay? Now, what we're going to do, I know it seems a little goofy, it'll make more sense when we're going to do a few examples of this. Okay? Remember, how do we determine this? Experimentally. So here's an experimental table that we are going to look at and discover or come up with the rate law. First and foremost, I want you to write this down somewhere. Write that down somewhere. Okay? This is kind of a template that we are going to use to determine the rate law looking at the experimental data. Okay? We are going to compare to figure out the rate order. Now, we have 3 trials here. This is my reaction. These are my concentrations of these particular reactants, and then the rate when it's at these concentrations. If I wanted to study how one thing affects the rate, would I want both of my reactant concentrations to be changing? No. Everybody understand that if I want to study one of the rates based on one of the reactants, I shouldn't have both changing their concentration, should I? Okay, so what we're going to do, please follow with me. If you stay with me, I think you will find this isn't as bad, but if you doze off and don't pay attention, this is going to be extremely hard because you won't know the process. Okay, because you can't put the process on a note packet. Stay with me here. So, which one do you want to find the order of first? You choose. Okay. Okay, so Rachel wants to find the order of NO2 first. If I want to find the order of NO2, wouldn't I want the concentration of NO2 to change, but the concentration of CO2 to not?
Yes.
Which experiments do you have the concentration of NO2 changing, but CO2 not changing? Everybody see how in 1 and 2, the concentration of NO2 changes, but the concentration of CO2 does not. We don't want this to change because we want to study the effect of a change in concentration of this, not of this. Okay? So here's how you do it. Okay? How did the concentration change?
0.5 moles.
Okay, but by what factor? Well, I want to know by what
By
factor.
2.
Does everybody understand when I say how does it change, then I want to know the factor. Okay? The reason why I want to know the factor is because we're going to put the factor into this. Okay? So, you said that it changed by a factor of 2. I'm going to put 2 here. Okay? Now, let's look at the rate. How did the rates factor change? It's always going to be a whole number multiple. So if you don't know, plug it into your calculator.
No.
Or 0.019 times what gives you this?
4.
It's 4. If you don't know, plug it into your calculator to confirm. But it's 4. So what we saw, we doubled the concentration and the rate changed by a factor of how much?
4.
What is the order?
2.
2. Oh. We're trying to find the order by seeing how the rate, or the concentration, affects the rate.
You're just solving for X. Everyone. Okay, cool.
Oh,
Are you seeing it, everybody? We said the concentration doubled, the rate quadrupled. What's the order when I'm just determining what this concentration is going to do? It is going to be second order. So I can start by putting rate equals, we know everyone's going to have K in it. And then I'll put NO2 and second order. Now I'm not done, I got to find the order of the other guy, correct?
Yeah.
Okay, so if I want to find the order of the other guy, what has to be true? Okay, so I want to find the order of him. Stay with me, I know it's a Wednesday. Okay, but this will be real easy if you stay with me, and it'll be extremely difficult if you don't.
So the order is 1.
Okay? Stays the same?
Yeah.
What happens to the concentration here?
Factor 2.
Double. Okay, so I'll leave 2 there. What happens to the rate?
2.
2. What's the order?
1. 1.
1. Everybody see it? Concentration doubled, rate doubled. That means if I tripled the concentration, the rate would then what? Triple. And if I increase the concentration of that by 10, the rate would increase by 10. So it has to be what order? First. So my rate law for this guy will be this.
How do you get 0? Oh.
There's my
No, I
answer.
said.
What's
you
K?
get 0.
Right there.
What's K?
K is just an experimentally determined constant. If I wanted you to solve for something, I would give it to you.
Are we ever going to plug in the thing for this chapter?
If you take advanced chem, absolutely, but I don't think for this chapter.
Yes.
Questions before I move on. I'm gonna do one more and then have you do one. Right? Here we go. Same idea. Now I just said A plus B gives you AB. That's no big deal. Okay, we know every rate law starts like this. And then I gotta find what the order of this is and what the order of this is by looking at the data. You guys look so tired.
We are.
Can you imagine if I came in looking like you guys?
You do.
Really?
You just better hide.
Normally, not today. You look great.
Normally I look tired.
Yeah.
Skype. That's a lie. That's a. Hey, you're standing up.
True. Stand up then.
Get up.
Shut up.
Dance.
Well, getting.
Alright, let's try to find A, which means what has to be constant?
B.
B, so which trials?
1 and 2.
1 and 2. Okay?
By a factor of 2.
A increases by a factor of 2, so the concentration doubles. The rate what?
Doesn't
do anything, so
Same.
0.
Doesn't change, so you would say that, well, you can,
Well,
okay, well, what, x to what gives you 1?
0.
1.
0. 0.
Everyone put in 2 to the 0 power in your calculator.
It's gonna be 1.
What's 1?
Anything 2 powers.
Put anything to the power of 0, what's your answer? 1. Okay? Now, listen to me. This should also make sense. I changed the concentration, did it affect the rate at all? If it doesn't affect the rate at all, then it has to be zero order. Has no effect. So, I don't even put it in the equation if it's zero order, correct? Just
Yeah.
leave it out. Okay? Let's look at the next one then. Okay? We're trying to keep A constant to find what happens to B.
It doubles.
Doubles,
Doubles. And then that.
and then
Doubles.
doubles. So what's the rate order?
One.
Oh, there's your answer. Is it starting to come to you?
Well,
A little bit. This is where I want to spend some time talking about this.
Tomorrow.
This won't take very long. This won't take very long.
I thought this said 10 because the wires right here.
Notice what they gave you.
Oh, they gave us the.
They gave you the rate law. Then they want you to answer some questions.
Oh, no.
Okay? What will happen to the rate if, okay? So, if you change the initial concentration of A, if you double the concentration of A, how will the rate be affected?
The
It
order
will be
of
affected
A would
double.
be 2.
directly.
Remember here, Gage?
Doubly.
If I double A, how will the rate be affected?
Directly. Double.
It's still the first order, so if I double A, rate will be double. If I quadruple A, the rate will be quadrupled. If I increase A by a factor of 10, the rate will go up by a
Factor of 10.
factor of 10. Okay? What if I cut A in half?
The rate will.
If it's first order, the rate will be half. Okay? What if I double B? Ooh, what would it be?
Would be it'd be 8.
8 times faster. Are you guys not seeing it?
Yeah,
Oh.
2 in with the B.
2 goes here. 2 to the third power is?
8. That's okay.
Okay, how about this one? What happens if I triple?
Then it's to the 27.
Yep. 3 to the third power is what? 27. Okay? So remember, the order tells us how much of an effect changing the concentration will affect the rate. This was our last one. Let's see if you guys can do it as fast as you can.
30
Once you find the process, guys, of this, it should go relatively quickly. I actually don't even have a key for this.
A's.
Take your time.
We out.
Did you get it, Gage?
I got it on time. I think I know what it is.
Yeah.
Do it and then see if you got the answer on the board.
Wait, so we don't have homework? We just have to send pictures? Or do we have homework?
There's definitely some homework.
You have homework.